given an interesting function here, 10 e to the minus 0.25x times sine x for x is greater or equal to 0. We're asked to show that the x-coordinates of the turning points of the curve, this equation satisfied tan x equals 4. So let's differentiate, find f dash x or df by dx. For this, I'm going to need to use the product rule, so I'll call this one u, this one v. Then u dash, I'll do 10 times minus 0.25, that's the bit I bring down. Actually, that's going to be minus 2.5, e to the minus 0.25x. And then v dash is going to be cos x. We get u dash v plus u v dash, which is going to give minus 2.5 e to the minus 0.25x times sine x plus uv dash will be 10 e to the minus 0.25x cos x. And this equals 0 for the turning points. What I can do is divide through by that e to the minus 0.25x. It's always positive. So, and then I'll add the other term onto the left-hand side. So I'll get 2.5 sine x equals 10 cos x. So I basically, divided that through and then added the first term onto the left-hand side, or onto both sides, I should say. Now I can divide through by 2.5, so sine x is 4 cos x, and finally divide through by cos x, giving us sine x over cos x, or tan x, equals 4. So it's the graph of h against t, where h is the modulus of that original function, showing the long-term behavior of the curve. So what happens with the modulus is that if it's positive, it does nothing. So in fact, the curve is going to entirely trace this bit here. Then if it's negative, it makes it positive. So it's a reflection in the x-axis, essentially. And then this will carry on. Of course, I'm doing it over the top. You're meant to construct a little plot yourself, but as long as it's got this kind of behavior, that's what we're talking about. So it's going to look like this. Now the function h is used to model the height in meters of a ball bouncing above the ground t seconds after it's been kicked. Use the model to find the maximum height of the ball above the ground between the first and the second bounce. So first bounce is here, second bounce is here. We're trying to find, well, first of all, the time when this takes place. Then we can sub that in to work out the height. So this is going to be when dy by dx is 0, i.e. when tan x is 4. Note we're using radians. We've been differentiating trig, so make sure you put it in that mode. And then we can do inverse tan of 4. That gives 1.3258. But that's actually going to be my first turning point here. So to get my next one, I just need to add on pi, because remember your tan graph? So I've got this value here. The next one, because tan repeats every pi radians, I just need to add pi on. Or with your cast diagram, we've got this one here. We're trying to find that one. So we've got our angle, we just add on pi to it. Which gives 4.4674. So that was the first. This is the second, or the second maximum height is what I mean. I don't mean the first bounce or the second bounce. I mean, sorry, I should probably clarify that. So this is This is between the 0 and the first, and this is between the first and the second. And then I can just put that back in to my function. I'm expecting to get a negative, so I'll just then make it positive. Okay, unless I put the modulus sign around it, which you can do. There is, I think, somewhere an absolute value button, but okay, I'm not going to worry about that. 10 e to the minus 0.25 times my answer, multiplied by sine of my answer, minus 3.1753. So to three significant figures, 3.18 meters. Finally, we're asked to explain why the model should not be used to predict the time of each bounce. What is going on here? If you think about the curve, it's this negative exponential is what is causing it to kind of follow this slope. That's what e to the minus 0.25x would essentially look like. The sine x is what is bringing in the periodicity. But the thing about sine is that it just it oscillates every 360, or in fact it goes up and down every, well, that is just 180, or I should say pi radians. So the times are always the same. This time period is the same as this time period, and so on. So we just have to basically refer to that. So model predicts time is the same between each bounce. Now, if you bounce a ball on the ground, that will not happen. As it gets closer and closer to the ground, the time reduces because it goes up by less and down by less. So, in fact, you'll see it taking a while, but then getting less and less, and it'll just like then do lots of little bounces right at the end, probably if it's a bouncy ball. So model predicts time is the same between each bounce, um, whereas it should decrease over time. Okay,